we're on to question 4, which uses a spreadsheet. We have access to the spreadsheet file q4 dracaenaplan.xlsx. You also need to refer to the information in the pre-release material, or known as the data booklet. So this is a question using a recurrence relation, and we are modelling carbon dioxide concentrations over time using the percentage change, the percentage decrease per day, followed by an absolute increase. Let's have a look at the pre-release material. You would have got the chance to read through this before the exam, so there wouldn't have been a time pressure in that sense. Much of this information is not particularly relevant, such as what Dracaena plants are, what they remove from the air, such as formaldehyde, benzene, trichloroethylene. I'm not sure if I'm saying that right. Carbon dioxide. The important parts which we will need to use later are these standards for very good indoor air quality and poor indoor air quality. And likely we'll have to make some judgment as to what kind of air quality we have got. Also, having this information in advance means we don't have a completely meaningless question, and it's easier to understand what it's about. So in the first part A, we need to complete the spreadsheet, and likely we'll be using these numbers: 13% decrease each day and 180 increase per day, and also this initial value of 2000 parts per million. Here's the spreadsheet. You can see at the top of the sheet there's a box to fill in your name, Scottish candidate number, and the name of your centre, which means the name of your school if you're doing this in a school. You see we have much of this information in here already. The 2000 for the initial measurement of carbon dioxide, 13% reduction, and then each day or each night we have an extra 180 parts per million added on. Now this question, the 13% refers to a 13% reduction. These recurrence relations will either come two ways. It'll be a percentage reduction and an absolute increase, or it could be a percentage increase and an absolute reduction. So what we have to do is work out the percentage which is left before we do the formulas. So 13% is taken away each day, which means there's going to be 87% left at the end. On a spreadsheet, the number 100% is represented by the number 1. So 1 minus 13%, and you will get the 87%. Now we can fill in formulae for the levels of carbon dioxide over time. So this will be based on the previous value. Day 1 value is going to be based on day 0 value. So first we'll take the percentage change. So you do that by multiplying by the percentage which is left. We are going to use that 87% every single day. So that will be an absolute cell reference. So press F4 on the keyboard, you press Fn F4. And then it's an additional 180, so we add that on. And again, that has to be an absolute cell reference. So now we fill this down to the number of days that we need initially. So highlight first, then drag down a small white box with a small black cross, and get the exact number of days that you need. For that cell to say the level at the end of 30 days is just a cell reference to your final value. So let's see that again. Fill it down, get the final value, and then reference that cell, and we get the value there. We will in fact also need to fill this down for more days in a later part of the question, so we'll just do that now and drag it down to I believe 60 days. we don't necessarily need to do this, but it just looks a bit untidy with all these extra decimal places. So there's a button you can press on the ribbon, that one there, I think adds on decimal places, and the other one takes away decimal places. So we want not that one, it takes away decimal places, and 1 decimal place is nice enough. We also need to add a chart, a graph showing this. So you do this by going to the insert, and under charts, it's not the line graphs, it's the scatter graphs you actually need. So scatter graphs with lines joining them, that one. And it immediately gives you a preview of what it will look like. So all we need to do is add on some captions. That's done with the plus, the very thin plus symbol on the top right, and we're calling them axis titles for the labels on the axes. And on the vertical axis, it's carbon dioxide in parts per million. On the horizontal axis, it is days of a day. And the title could be something like carbon dioxide over time, a graph of carbon dioxide on a day. That's done part B as well. We have completed the 60 days and we have done the graph. And don't forget at the end to print it in value view and formula view. You would just do the printing for parts A and B together. So you have that reminder at the end of the question to do that. Before we go into part C, let's have a quick look at the marking scheme and some notes about rounding. Now in this question there is no point in using any rounding functions at all. Parts per million concentration of carbon dioxide is a continuous quantity and there is no sensible reason to round it to the nearest parts per million. However, if you did use round, then they would give you the mark for it. Really, the main place you would be using the round function in this course, as far as I'm aware, would be for rounding interest calculations for money. If you used int, you would have lost a mark. Int, as long as it's a positive number, would always round it down. So it's saying that that's not justified. There's no reason always to round down to the nearest parts per million. And I suppose that would give you a kind of bias on the model which wouldn't be appropriate, whereas round sometimes would round up, sometimes would round down. This is a point that does confuse people for recurrence relations, that you do really have 3 different possibilities. You could be using int, round, or no rounding at all. In part C we have to make this comparison and decide whether the Dracaena plants are effective in the long run at obtaining very good indoor air quality. This is when we need to look at the data booklet information and use this 800 parts per million, which means if it's below 800 parts per million, we have very good indoor air quality. So we found from our modelling that in the long run, it only tends towards 1384. So the conclusion is, no, the plants do not give very good indoor quality. So the plants are not effective, you're answering the question in the terms that it's asking you, at obtaining very good indoor air quality. And that's not enough, you have to actually compare numbers. They need to know you've looked at the data booklet, so you have to reference the 800 parts per million, and it would also make sense to reference the long-term trend. So the long-term level is 1384.8 parts per million, which is greater than the 800 parts per million required. So that's that question finished. I hope you enjoyed recurrence relations.